Okay, let's start with the last class about stability. In this case, the stability is quite different because we'll talk about something that is connected with the stability of movement, but not exactly a stability of the stars. That is the convection. Convection is the movement of material inside the fluid. Some part goes up, some part goes down, and essentially it's an energy transfer phenomenon, but is connected with the stability, dynamical stability of the gas. So it's in the between of two phenomena. Essentially, we can describe the starting point with the classical equation for the luminosity transfer, where the luminosity has certain radius multiplied by the opacity divided by the area of the radius. So essentially, L, this is the flux of energy due by the radiation, is equal to this value that is a constant. And at the end, not exactly. This is part is a constant, the temperature, the density, and the gradient. With the minus, since the gradient goes, temperature is higher in the center and lower side, so decrease. Observing, we can understand that essentially a certain pair of data, gradient and opacity, leads to a certain value of the luminosity at the distance when the flux due to the radiation. But also we can see that if there is a certain luminosity, that remember this is determined by the what is connected with the nuclear luminosity, the energy produced by the nuclear reaction, since that this is the flux can change with the distance, but the L is the total energy of a certain distance, and is more or less constant if there is in that area there are not source of energy. So if you have viscosity is negligible. If outside the core, where there is the nuclear reaction, the luminosity is essentially constant. So this one can be calculated inside the core, and we know that this value with the opacity lead a certain gradient of temperature. Because if you have a really high luminosity, you need a higher gradient of temperature because you will have a lot of energy inside. That is internal energy, so temperature. Or if you have a high opacity, this means the opacity stops the radiation to pass, and there is more higher interaction of the radiation with the matter. That means that matter will have higher energy. That means high internal energy, more a lot of microscopic movement, so temperature. This increase where the capacity is high, so the gradient will be steeper. This is also the reason why this relation said that the radiative luminosity transfer relation equation, it's a two-way equation because you have certain gradient, opacity, density, and you will know how much is the luminosity permitted, or what is the luminosity that will be with that value, but also you have a certain luminosity, a certain opacity, and you'll get to know how much is the gradient. This last is important because you cannot increase the gradient luminosity, this absolute value, actually to be more clear. Okay. Mathematically, you can increase from -2 to -1, but in absolute value, it decreases. The gradient is absolute value cannot increase at pleasure. This is because above a certain value, we know that convection will start. There will be some movement of blob, of mass, of gas that will move due to the higher, to the high temperature gradient. So convection is a type of dynamic instability, but is quite different because it's without the disruptive consequences. It's not like the thermal instability or dynamic, classical dynamic instability where affect the start and expanding, contracting. How is affected? Essentially in two ways. One is a really effective heat carrier. It's one of the best way to transfer the energy, really good. And the other is a mixing mechanism. Since it's there is a mass goes up and mass goes down, is permitted to mix whereas working the convection, and to have uniform composition of the area. So, as I said, it's not a disruptive consequence, mainly because, on the contrary of the other instability, there is not a net mass flux. If you calculate the mass with the velocity as a vector, and divergence, it's zero. It's some part is going up, some part goes down. It's like in magnetic field, where the line as much line goes out, also back in. So there is not a net mass flux, so you have no contraction or expansion. Let's say as much as it flows up, as much as it flows down, it's maintained. Everything is about essentially the buoyancy force, as well known in classical physical class. The buoyancy force is given by the difference in density multiplied by the volume of the we are considering, and the gravity acceleration. Essentially, the density, the difference among the density of the environment and the density of the object we are considering. So if the object is lighter, will goes up at higher value of the radius, so positive. If it's heavier, more dense, will sink down, since it's negative. As a result, if you consider the acceleration, this one divided by the mass of the object, that means that density multiplied by the value, we have that the acceleration of the object is essentially the acceleration, gravity acceleration multiplied by a relative increase of the density. Yeah, relative difference on increase of the density. So we'll consider we have in the position 1 a blob of gas. There in the position the environment has density 1 and pressure 1, and this object, this part will move up for the buoyancy force up to a position 2 where there is density 2 and pressure 2. Well, this because there is have a delta temperature in the receive more temperature that causes density decrease, so it moves up. We'll consider always that in the movement there is pressure equilibrium among the object and the environment because it stays in equilibrium. That also means that the velocity of the object has to be less than the velocity of the sound. That is the velocity in how a pressure wave can propagate, because it can move in supersonic, that pressure cannot be maintained equal because the pressure cannot communicate this value, essentially. So the movement in the convection will establish that are always subsonic. If you go from 1 to 2, then we have to check and see what happened. If in position 2, the object will, this blob will goes up again, so there is instability, or will go back, so this means stability. If the density of this part is higher than the environment, then you see here, this is higher, this is negative, so the buoyancy force will be negative. That means that the distance will decrease, so we have stability. If instead the density of the object will be less than the environment, so we have the for this increase of temperature, the density will decrease and will start to move. After certain distance, we see that the density will, since there is equal in pressure, will decrease, but check if decrease more or less than outside, and if it decreases more, so still is less than the environment, the buoyancy force will be positive, so the radius will increase again and we have stability. This is a condition to the convection will start and continue, not start and goes back, just a little variation. So before small oscillation, we want a perfect movement. In this case, we consider that the thermal time scale, thermal time scale, the time is needed to thermalize the object with the outside and have the same temperature to lose is internal energy, excess of internal energy due to the difference of temperature with the radiation will be definitely higher than the dynamical time scale. That means that in the time the object will move from up to here, essentially there is no leak in energy and maintain. It means that the heat are staying the same, and we have an adiabatic process. That means that for the object, P star, and the pressure and rho star, the density, are connected with the adiabatic relation. On the paragraph 6.4 of Kippenham, there is a nice demonstration that the thermal time scale is thermal adjustment time scale. It's definitely bigger than the period for the connected with the adiabatic frequency we saw yesterday on the oscillation. So we consider it's a good approximation that in this movement the classes are adiabatic. No use of energy during the movement, just at the end. So we consider a plot on this situation. Point 1, point 2, let's say that the pressure is moving outside, toward, and so the pressure in the second position will be less in the position 1. In red here is approximated the adiabatic. It's not exactly, just for reference. And we'll have the two possibility of how we can vary the environment with a way that is less steep than adiabatic, and the one with steeper than the adiabatic. You see here the tangential, the derivative is definitely, this is bigger than here. What we say that if the environment is less steep, like in this case, then in point 2, we have that the object have a density higher than the environment, so stable. If instead there is the process have a gradient that is steeper than the adiabatic, then the density of the environment will be higher than the object, so there will be continue the movement of the object, so instability for the convection. That means, so visually, that you need the outside in the star, in the area we are considering, the gradient should be steeper than adiabatic. To see mathematically, we can do the approximation. We have point 1. From here to here, we have a delta, certain value that is P2 minus P1. It will be negative, but in absolute value, it's positive because it makes it a little easier. So the density at certain point hereby is the density at the beginning less the gradient multiplied by this delta P. It is just Taylor approximation in this point. I approximated the function with the value in this point, the gradient in this point, a small variation. So anyway, we are just considering small variation to see the continuity of that. For the stability, we want that the density of the object and the density of the environment have to be higher than 0, greater than 0, so positive. This approximation is valid for both, so we substitute this two value in this way, and we have then so the gradient adiabatic, because for the object the gradient is adiabatic, multiplied by the different impression plus the gradient for the environment. Here is a minus, because essentially here will be P1 and P1 for both, and we already have take away. Here is minus the density, so will be minus P1. It is the same for the two, but it's the minus 1 became a plus. The gradient from the environment multiplied by the difference in pressure greater than 0. Delta P is positive. I define positive, so I can divide it different from 0 by definition. So I can divide it without problem, without changing the direction. I mean, greater or smaller. We move this on the other side, and we change the order of the two in this way. 1 divided by changing the order of the two variables, because we need to have pressure on density. Usually we have C in this way, and we'll get so this result, and we saw before that for instability, the gradient of the environment must be less than the gradient of the adiabatic. Why using this? Because, okay, if you multiply by density divided by pressure in both sides, we'll get the classical coefficient, adiabatic coefficient, in this case the gamma 1, that is the logarithmic gradient among pressure and density. That is going this way, and for stability we need that this coefficient must be less than the gamma adiabatic, the classical. The gamma 1 is the generic, that is equal to the gamma adiabatic only when we have adiabatic process, obviously. Then the other quantity used are the gamma 2 for the usually also represented with just the symbol of gradient. That is the adiabatic gradient, logarithmic gradient among temperature and pressure. That is gamma 2 minus 1 divided by gamma 2. That to be less than gamma adiabatic coefficient minus 1 divided by the adiabatic coefficient. Remember also this situation that came from the ideal gas equation state. We know, for example, that for beta that go to 0, the two will be similar. Also, beta to 1. Let's see later. Actually, here. Then, as we saw, so the convection depends when the gradient temperature is in absolute value greater than temperature gradient due to the adiabatic process. That means that the instability of the convection is easier anytime in the condition that cause that this coefficient to be slower. When all the process also we saw before yesterday for the dynamic instability, when there is a process, a condition that will lower the adiabatic coefficient, That means also that the convection will be easier to be installed. It means that we can have a partially ionized gas at the lower, as we saw, can be definitely lower, instead of the fifth third that are 1.7. The ionization can bring it also to 1.2. Or if you have the beta that is definitely smaller than 1, that means that radiative pressure is more important than the gas pressure. Here it's to some condition. Also remember that even if the gamma 1 and gamma 2, these two, are have the same limit for beta go to 1 or the beta go to 0. Get 1 here, both the value are 5 third, here both value are 4 third, but the function of the defined respect to the beta, beta variables, are different. That also means that essentially, let's say these are the values connected to this gradient, but they are equal in not always the gamma 1 is the diabatic coefficient of this value, but just in certain situation with the diabatic process. So as I said, we have the logarithmic gradient of the temperature must be less than the adiabatic coefficient minus 1 divided by the coefficient. Then we can divide, split the two, and in this way we split the two, put in the R and the R, so we have a gradient, temperature gradient, in radial gradient of the temperature and the pressure, and with the minus to maintain everything positive. So we have this value that's going to be less of that value. And if you can, as so before, the gradient, radial gradient of the temperature, the minus gradient, is inside the relative transfer equation. When we know that the radial gradient of the pressure is inside the static equilibrium, we put this value obtained from this formula inside, and we got this one. So a relation, bigger relation among the two. Here we have the density and the density. We can take away the radius and the radius. We can take away the temperature. We go back. We regrouped everything, and we have actually little simple luminosity and certain radius, not the luminosity outside, even if outside the core is the L is more or less constant, multiplied by the opacity, and must be less than the constant, the mass and the radius, and the part due the coefficient, and this one. I regroup here directly because for A divided 3 multiplied by T to the 4 is the pressure radius, the radiative pressure. That divided the total pressure can be seen and directly as this way, 1 minus beta. So we have this value. For P Greek CGM, for this situation, and this value is okay, not luminosity of Eddington, but because multiplied by the opacity. But okay, I always say that check the equation. Sometimes they are putting an error. It makes sense because this cannot be, this is a constant and a dimensional value. Here we have luminosity by opacity. You cannot have luminosity on the other side. Must be opacity also here. But anyway, essentially this one is important. What happened to the pointer? Okay. Luminosity by opacity must be minus this constant, more or less. This is the mass, but okay, constant, and the dimensional. Since we can see that for beta more or less 1, this goes to 0. The gamma is for third, and this everything goes to 0. This is a bit higher, but this one goes to 0. For beta, more or less 0. This goes to 1. And this is going to 1, 4. 1 divided 4. So multiplied by 4 is 1. So this is 1. Essentially, this changing with the beta, they are also connected with the adiabatic coefficient, so are not essentially two values. These parameters are disconnected. These here vary on among 0 and 1. So consider multiplying by opacity here, we see that the condition is smaller than condition for instability of luminosity of Eddington. Here, I said, forgot that it's disappearing the pointer. And I don't understand why. What's happening to okay. That means, as I said, the convective instability occurs before instability by radiation. This is a stronger situation that will start the convection. As we saw, some causal convention can be an opacity really big, because this is the condition for the stability. So if this part is too high, too great, we are instability for the convection. So can be all opacity really high. Typical star envelope for outer layer due to the ionization or opacity to bound free, or to have a really high luminosity. When they are really high, so we have the burning process with the high nu, that is the exponent for the temperature. Typical in the core where we are burning the hydrogen with the CN cycle. PP cycle is not so strong in the energy production, so not present in small stars. We need usually to be two solar masses or more, or also burning in the shell. The shell burning shell are usually going with the CN cycle or helium burning that are really depending on the temperature, so and can produce a lot of energy in that small area. So essentially, we can have convection, essentially high opacity, mainly in the envelope, convection in the envelope, in the outer part principally, or where is cooler. So we have hydrogen not really completely ionized, or in the core, in the convective core, due to the high production of nuclear reaction. Remembering the energy production rate can be expressed as a constant multiplied by density of a certain lambda, the temperature of the nu. We wanted that this will be really high. The luminosity, this value is just this epsilon integrated on the mass we are considering. Calling the same one of the point source model that essentially is well connected with the star that are producing the energy in the core with the cyclone CN that is really well producing a lot in that area. Calculating the new value for the instability, and we see that if you consider in the opacity that is almost constant, Thomson scattering, electron scattering, that nu must be 3 and 4. Or in with the Kramer opacity, the nu must be greater than 8. There are this typical value, actually. This can be also proton-proton, but nu greater than 8 is perfectly for CN cycle and helium burning in all the others. And beta that is more or less 1 with the pressure, so essentially the pressure gas are most important. It's easier, as we saw, remember here is 1 minus b, so when beta is 1, this is 0, so essentially it's relatively easier to have when the relative pressure is less important, it's easier to have stability by the convection. From the quadratic Eddington quadratic equation, we know that the beta is a function of the total mass of the star, and this is supposing that the beta is almost constant in the star. So if for m minus than 1 solar mass, this value is almost 0, so we should have convection. And in fact, star like the sun start to have the outer part of the envelope with convection, and the stars with the lower, this convection start to penetrate deeper and deeper and deeper up to the smallest star. They are essentially completely convected. They are burning just in the center, and the convection will feed all the hydrogen. This is peculiar, that are stars that terminated their life essentially as white dwarf of helium, because among the convection and the new induction burning will consume on the hydrogen present in the star. Then we stop there because if you will see in the evolution, if you don't have enough iron mass, you can break the degeneration on the electron, and you cannot compress too much the stars. It will not reach maybe the temperature for the universe. The same low mass stars will be stable for convection, especially the outer layer. So essentially, we saw that convection will be inner part, the core, especially for the high mass, for the more massive stars, and for the less massive stars, the convection will be in the external part. It makes sense because smaller stars are cooler, so it's easier that outside the envelope will be at a lower temperature than we needed to completely ionize hydrogen and helium. Then so the ionization is partial, and we have an higher opacity. Vegetal matter is definitely stable. Two reasons. One is highly conductive. The opacity for the conduction, as we saw before, is definitely, for this reason, is definitely smaller than 1. That means can permit and higher. That makes sense because, as I remember, the opacity by the density, the opposite one divided opacity and density is the mean free path. And to have an highly conductive matter, you need that the mean free path will be the larger possible. If it is possible, because so opacity really small means a larger mean free path. And also we saw that usually we describe the conductive transfer rate, transfer equation, in a similar way that is the equation that is written for the radiative transfer energy. Also because both depend on the gradient and temperature and some constant multiply. So the density, so we put all the characteristics in this constant, but the opacity are summed with the inverse. So the total opacity in radiative and conductive, it's his 1 divided the opacity is equal to the sum of the inverse of the other two. That means if the conductive is really small, this will be really big and will more important that the part is due to the radiation. So the conduction will manage essentially all the energy transfer rate, and the gradient will be relatively smoother because they essentially, in fact, degenerate core usually are isothermal because the conduction is so well working, but also is not stable, is missing the L. By nuclear reaction, and there is no stability for nuclear reaction. So if when start the nuclear reaction will disrupt everything, will disrupt the degeneracy, or will disrupt the stars directly. So one part of the star is in degenerate state, there will be no convection because all the gradient is definitely smaller, or there will be instability, dynamic instability or thermal instability that will make no sense for the convection. If you study, you see the convection in the inner part is really efficient. That means the gamma is definitely similar, equal to the adiabatic value. If you do a calculation, we can considering the everything starts because of the excess of temperature, considering this relation between the small part, and that the pressure maintains the same, so the delta P is 0, so we have just a relation here. We have the delta rho, so rho it's equal to this one. We introduce this value for the delta temperature. Lambda is the apical size of the cell that actually is what is the center of the convection, of the theory about the convection. In fact, lambda is both the typical size of the cell that is moving and the typical path of the cell they are moving. And that is proportional to the scale on which the pressure are changed, essentially on 1 over E, the constant of Euler constant. And everything, this is what is called the mixing length. Calculating this value is really important for determining all the convection. It is quite complicated. Here the luminosity and this distance, the size, and as it's moving, the cell, the velocity they're moving, the internal energy by using mass and multiplied by the mass of the convected cell. The difference in temperature is proportional to this amount of energy. So this is time. For energy by time, we get an energy. The temperature center position is proportional to the internal energy in that position. We can calculate everything. Velocity can be calculated with moving, start from 0, arrive to a certain position. So the acceleration moving multiplied by the typical path size, that is this value, as said before, the gravitational acceleration multiplied by relative difference in density, multiplied by the lambda, that must be smaller this value, because otherwise the pressure cannot be constant in the movement. And at the end, we get the situation show us that actually he should be okay. Definitely the value of the difference in temperature respect to the difference changing here with luminosity, we can change as a solution that instead of this is the total energy, thermal energy for the cell, luminosity, approximation of this one. This value are essentially, as you saw, this is the total energy divided by luminosity is the Kelvin-Helmholtz time scale. This is the dynamic time scale. This is just to have an idea, and we got to the difference relative is really small. So in the inner part, where we can do this kind of approximation, the difference change are not so great among the cell and outside. That means that when they are starting the convection, the gradient of the start is essentially the gradient of the adiabatic gradient in temperature. This is true for the inner part, for the core. That means if it is essentially adiabatic, everything, there is a polytropic relation, because the relation among pressure and density can be seen as the one for the adiabatic. It means that the pressure can be seen as only depending on the density. In the outer part, cannot be more do this approximation, so the gradient will be higher. In fact, it's more complicated to calculate, to elaborate on the convection outside, in the outer part, in the outer layer, than the inner part. In the inner part, you can directly go with the supposing that the gradient of the star, where is in the core, where there is convection, you can suppose the gradient is just the adiabatic. Make it easier. At the end, we can see the delta temperature in this value, the difference in the gradient multiplied by the lambda. This is in general. And the flux for the convection is 1/2, because we have half cell goes up and half cell goes down. The density multiplied by the velocity, the capacity of the pressure constant, and you say the process happen when the pressure that is constant multiplied by the difference, that is this one. And supposing that this nabla R is the gradient if all the flux is just given by the radiation, is the theoric gradient if there will be only radiation to transport the energy, so the convection are not possible to be activated. We see that the flux of the convection is the capital flux divided by this two. So strong there is this difference among the actual gradient in the system and the gradient suppose if there is only radiation, the higher is convection. And here we are giving you some example of value for convection in the inner part, in the core, and the outer part in the envelope. The difference in temperature here inside is said here really small, just 1 Kelvin, but it's really good enough to transfer. And the outer you have definitely in a bigger difference, because it's not so effective. As we saw below, is 100, 1000 Kelvin among the two part of the upper part and lower part of the convection. The velocity only respected to the velocity of the sound below in the core are really small, while outside it's more near to the velocity of sound, cannot be higher, as I said. This is because here you need a higher velocity to move. The typical distance is 10 to the 5 kilometers in the inner part and 100 kilometers outside. This seems really big, but actually is just 1/7 of the radius of the sun. So it's, and we know that the core of the sun is more or less 1/3. So it's small, actually. The velocity, if we see, is in the order of 100 meters per second, while outside definitely higher, as said before, it's the order of kilometers per second. The typical time to move the cell is some days down, because it's low. Here is really quick, few minutes. And you look at the efficiency inside, the efficiency is definitely big. It's really good to transfer, even if the temperature is so small, it manages to be really efficient and permit to have the gradient of the star that is essentially the bottom. Outer parts are not so good, and so the gradient will be higher than the adiabatic, but less than this value. In fact, there is a relation among this will be higher than the gradient of the adiabatic, the gradient of the environment higher than the one of the number of the object. No, the object, this is bigger than the object of the environment, and the environment of the adiabatic. Okay. We'll finish a little before. Since I don't think there is question, if there is no one connected due to the strike, I will stop here and determine what to do. Tomorrow should be the exam, but doing the exam the day exactly I finished to explain. Sadly, last week we lost by strike. The next week is the break given by the university. So let's see what we do. See you.